If you recall when we started studying statistics, we studied some kind of basic things. Like we studied the concepts of nominal and ordinal and what else? Ratio. What was the other one? The types of data that we can deal with. Nominal, ordinal, ratio, what am I forgetting? Interval. Okay, remember we studied that. So after that, we started to talk about other concepts, more kind of practical concepts, like we ended up with standard deviation and correlation. But at the beginning, we talked about these concepts, and we also talked about the difference between correlation is not causation. We also talked about that. So these were kind of basic concepts, and then after that, we went on to more kind of, I don't know what to call it, more non-basic ones. So in the same way for probability, we're going to be studying probability now, which is not statistics. And for probability, we're going to study some very basic concepts first, and then use those basic concepts to study further. So just like it was important to know the difference between these types of data, types of variables, it's important, and also it's important to know about causality or causation. And remember, we ended up talking about treatment groups and control groups when we talked about causation. But same thing for probability, we're going to need some basic concepts. So let's imagine some examples. Well, let's say that first of all, well, let me bring this up actually. Let me bring that up. Where is it? So, and I will be calling on people today. And so you should be paying attention. So, but let me just bring up one thing here. Show you one screen. My computer will speed up. Let's see. Just a second, it's just taking a long time here. Okay, let's see, it's here. Okay, so here you can see so probability can be used many places, but it can certainly be used in business. And so here we have some situations where you might use probability. So we have managers often base their decisions on analysis of uncertainties. For example, what are the chances that the sales will decrease if we increase prices? So, if you're a manager, you might want to increase your prices, but you're also afraid that sales may decrease too much. So you have to sort of balance, and you don't know what's going to happen. So that's called uncertainty. You're not certain about what's going to happen. And so that means we're interested in probabilities. We might be interested in probabilities. Or here's a second example. You make a new assembly method, and you're hoping that you're going to improve productivity. So also, you don't know if it's going to improve or not. So there's also uncertainty there. And so that also brings in the concept of probability. Or if you make an investment, so you don't know if it's going to be a good investment or a bad one, and probability can also be used there. So we do use probability in business, and so that's why I guess they are teaching it at APU in APM. Okay, so we're interested in this concept of probability, and probability has to do with uncertainty. Uncertainty, yeah. So we're going to start with some really basic cases, not so sort of complicated as whether if you increase price, whether sales will decrease. That's kind of very complicated. It's hard to know the answer to that, hard even to think about it. Or changing the assembly method, will that increase productivity? That's also difficult. Or in making an investment. So we're going to reduce these kinds of questions. We're going to focus on really basic questions because you can't start out on the hard questions. You have to build up. You have to build your theory from basic questions first, and then hopefully you can kind of extend them bit by bit to cover more complicated situations. So we're going to start out with simple or kind of basic situations. For example, we will start out with where you just toss, or say, yeah, toss a coin, or roll a die, or toss 2 coins, or roll 2 dice. Now, these are not really business questions, but we want to study this probability, and we want to make it kind of simple at first, and then we'll expand to how we can use it in a business setting. But we want to do it with something easy or simple first. So these are what we're going to start with. So the thing is that so anyway, so we're going to look at maybe these 4 examples, or there are other examples we can also look at. Okay, so let's first of all, we're going to call each of these, this is a kind of a weird word, but we're going to call each of these experiments. So we're going to talk about an experiment where you toss a coin, where you roll a die, where you toss 2 coins, where you roll 2 dice. And then so now we're going to ask, well, let's see. So we might, yeah, okay. So let's talk about what are the outcomes for each of these experiments. So does anybody want to give an example? I mean, I give the outcomes for this first experiment, tossing a coin.
2.
Okay, there are 2 of them. Okay, that's possible to say 2, but I want to know what I want to know what they are. So you could say heads, and you could say
Tails.
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 Okay, right.
50-50 count as an outcome.
What?
50-50.
What?
Like 50-50.
Oh, okay. Yeah, right now I just want to focus on what they are, not what their chances are.
Oh,
I want to do it very methodically. So we're going to say first what they are, then we're going to talk about what the probabilities are. So right now we're just saying what the possibilities are. So heads and tails, of course we could write, you know, H and T if we wanted to, or we could write H, comma, T like that. It doesn't matter. So any of those will be fine. And we are going to put these, we're going to write these outcomes in set notation. So what I mean by that is we'll put that and that. So we could say that, or we could do it here, same thing. That and that, or whatever. Okay, so we're going to say the outcomes are going to be listed as a set. So you, either this one or this one, either any of those are okay. Okay, and then now, how about the outcomes for this one? So let me put set. So what are going to be the outcomes for rolling a die?
The numbers 1 to 6.
1 to 6.
1 to 6.
Okay, 1, 2, 3, 4, 5, 6. Okay, good. Now, as long as we list all the possibilities, then we'll consider that a good description or good representation of the outcome. So here, this is all the possibilities, but there are other ways we could do this. For example, we might break it up like this, even and odd. That also describes all possibilities, right? You can either get an even or an odd. So that could also be called the outcomes. And let's see, what else? Anything else? Well, let's say those are two different ways to describe the outcome. So sometimes you might use this, and sometimes you might use this. So there's no, it doesn't. This is not better than this. They're both okay, but this turns out to be more useful than this in many cases. Not always, I guess, but in many cases. But it doesn't, in order to say the outcomes, we just have to list them all. So we listed them all by writing this, but we also listed them all by writing that. Now, you don't want to repeat anything. So here, I'm not repeating anything, and here, there's no intersection between even and odd, so I'm not repeating anything there either. Okay, now how about this one? So if we toss two coins, how can we list all the outcomes? So let me call on people instead. Okay, how about Hu Tai Nguyen?
Yes, Professor.
So what would you say?
So it's either both heads or both tails or head and tails.
Oh, good. What did you say?
It's either both heads, both tails, or head and tails.
Okay. So if I write it like this, I need to add one more. What is it? Well, okay, I see what you're saying. Okay, I'm going to write it like this also. Maybe
Yes.
okay. Maybe I see. You could have just said those three, I guess. But yeah. Anyway, this is one way. Is there any other ways? Like here, we had this and this. Anything else? Any other way? I have one other idea, but I don't know. I don't know. Anybody have any other ways?
Yes, Professor.
Yeah, go ahead.
Yeah. So like with even and odd, it could be like same or different.
Okay, right. Both are same. That's one. Both or each are different. Right. That's good. So that's another way to list the set of outcomes. Any other way? I have one more idea, and that is this one. I could do this 0 heads, 1 head, 2 heads. Okay, does everyone get that? That also works, because that's all the possibilities. You could get either 0 heads when you toss 2 coins. You could get 1 head if you toss 2 coins, or you could get 2. Does everyone agree with that?
Yes.
So again, none of these are better than any other one. They all describe the possible outcomes. So I want to write, when I write the outcomes, I want to preface it with possible outcomes. And actually, I want to preface that with all possible outcomes. So this is all possible outcomes. This is all possible outcomes. So is this, though. This is all possible outcomes. But so is this. And so is this. So they would all do as the set of all possible outcomes. And then this one, rolling a die. Let me go to here. And let me go to rolling 2 dice. Let's get a picture. So rolling 2 dice here. Put that in there somewhere. Okay, so that's rolling 2 dice. And so we also want to list all of the possible outcomes for that, but let's leave that alone for the time being. So we have, at least for these, we have 3 different experiments: toss a coin, roll a die, toss 2 coins. So by experiment, we mean something that we do where we don't know the outcome. So if you toss a coin, you don't know the outcome. So that we can call that an experiment. If you roll a die, you don't know the outcome. So we can call that an experiment. And if you toss 2 coins, you don't know the outcome either. So that can be called an experiment. So we have this word experiment. And then once we identify an experiment, like here, we have an experiment, then we can list the outcomes. So for example, that. Or here, we have an experiment, then we can list the outcomes, that, or maybe this. And once we have this experiment, then we can list the outcomes, like this one, or this one, or this one. All right? So we have the experiment. Once we have that, we can think about the outcomes. Now, there's a word that they use in probability, which I don't know. I don't like vocabulary, to be honest. I prefer just, all possible outcomes instead of making up some special word for that. But I didn't write the theory, so I can't say. So anyway, there's a special word for this, and it's called the sample space. Okay, so you have to learn that word. It just means this or this or this. These are called the sample space for this experiment. The sample space for rolling a die is here. The sample space for tossing 2 coins could be here, or here, or here. Okay, so that's the word, sample space. Okay, so we have experiment and sample space. So once we know the experiment, once we know it's toss 2 coins, then we can say, oh, the sample space is this. Or we could have said this, or we could have said that. So the sample space is not decided. There could be more than one possible way to state the sample space. Okay, now with these, with this definition and this definition, let's think about some probability questions. So let's suppose that we say, what is the probability of getting heads? And I'm talking about this experiment, tossing a coin, tossing one coin. So what's the probability of getting heads?
One half.
Yeah, it's 1/2, right? 1/2. Okay. Now suppose we're talking about this one. So suppose we roll 2 dice. So roll 2 dice. Okay, so this one was actually roll 1 dice. So here, rolling 2 dice, what's the probability of getting, I'm sorry, rolling 2, not 2 dice, sorry. Let me undo that. Rolling 2 coins, or tossing, maybe I better rewrite that whole thing. Tossing, usually we say tossing. So I'll say tossing. Toss 2 coins. And this one was toss 1 coin. So if we toss 1 coin, the probability of getting heads is 1/2. You toss 2 coins, what's the probability of getting 2 heads? So if we look at, we have different sample spaces. And like I said, some of them are more useful than others. And for this question, this is more useful. So this says that you could get HH, which means 2 heads. You could get TH, you could get HT, you could get TH. Did I say that right? HHTT, HT, and TH. Okay, so here we want to know the probability of getting 2 heads. So where is that in this list here? That is here. So what's the chance of that happening?
1/4.
Yeah, because there are four different possibilities here. And this is 1 out of the 4. So the probability will be 1/4. Now that actually doesn't necessarily follow though, because if these are not all equally likely, then this wouldn't be true. But I think we can accept that these outcomes I think we can accept this. These are equally likely. Okay, if you accept that, then if each one of these is equally likely, then the probability of getting 2 heads, there's only one of those that gives you 2 heads. So that person is walking with their, anyway, okay. So it's 1 out of the 4 equally likely outcomes. So that would be 1/4. Okay, so everyone get this? Now, if we had used this as the sample space, then you might have said, oh, I think the answer is what? 2
1/3.
heads. You might have said, oh, I think the answer is 1/3. So that would seem like a, that might seem like a reasonable answer, because you have 3 outcomes here, and 2 heads is 1 out of those. So it's 1/3. So you might think that the answer is going to be 1/3. But the thing is that it turns out that these are not actually equally likely. But it turns out that these are actually equally likely. So that's why this one is easier to work with, because then we just know that each one of these is 1/4. But if these aren't equally likely, we don't really know what they're going to be. It's not 1/3, 1/3, 1/3. So I don't know what it is. But if these are equally likely, and it turns out that they are, then it's 1/4, 1/4, 1/4, 1/4. Okay, does everyone get this idea?
Yes, Professor.
So when we toss 2 coins, what is the probability of getting 2 heads? 1/4. Okay, let's ask another question, a similar question. Let's say, again, toss 2 coins. What is the probability of getting let's say, what do I want to do next? I'm getting a head and a tail. So what's the probability of getting a head and a tail? So we go back to here, and if we agree that these are all equally likely, so let's just agree with that, even if you're not quite sure, but let's just agree that these are all equally likely. And with that, what would you say is the probability of getting a head and a tail? So does this have a head and a tail?
No.
No.
Does this have a head and a tail?
No.
No.
Does this have a head and a tail?
Yes.
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 And does this have a head and a tail?
Yes.
Yes.
Pretty
Yes.
much.
Yes. So how many of the 4 satisfy this?
2.
2 or 4.
2.
2.
Yeah.
And again, I said, let's assume that these are all equally likely. So if there are 2 among the 4 equally likely ways to get a head and a tail, then what's the probability of getting a head and a tail?
2/4.
Half.
2 over 4, right? Everyone agree with that?
Yes.
Okay, let's try another one with this same experiment of tossing 2 coins. Let's try this one. Okay, here's another question, the green question. What is the probability of getting at least 1 head? So let's look at it again. Is there at least 1 head here?
Yes.
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 Is there at least 1 head here?
No.
No.
No. How about here?
Yes.
Yes.
And how about here?
Yes.
Yes.
Okay. So how many ways are there of getting at least 1 head?
3 ways.
3, 4.
3 out of 4 equally likely cases. So it's going to be 3 out of 4, right?
3 out of 4.
Okay. So, all right, now we have actually 4 probability questions. We have this blue one, darker blue one. We have this gray one. We have this lighter blue one. And we have this green one. So we have 4 different probability questions. Now, are they, if you look at the English questions there, are they exactly the same? Are they exactly the same? No, of course they're not the same, right? But there's some part that's the same, but there's also some parts that are different. So which part is the same in each of these questions? What's the same?
Probability.
The first, let's see, the word what is in all of them, right?
Yes.
What else is in all of them? Is.
The probability of.
Is. So what's common to all of these? What is the probability of, and maybe getting, right? That's in all of these questions, right? Everyone agree?
Yes.
Yes.
Okay. So if that's what's common to all of them, what's different about them? So we have, what's different about this one? This word, right? Heads. What's different about this one?
2 heads.
2 heads. What's different about this one?
A head and a tail.
And how about this one?
At least one head.
Okay. So part of the question is the same, but part of it is different. Okay? So the part that is different, we're going to call an event. So we're going to, so let's write that down. Okay? So for the dark blue question, what is the event? Let me call on somebody. How about this person? Meg.
Yes, Professor.
So what's the answer?
The event of getting heads.
Yeah. So the part that is different is the event of getting heads, right? Or heads. So the event is heads here for the dark blue one. Okay, let me ask somebody else. Okay, how about for the gray one? What is the event? What is the part that is different? So that's Zoltron.
Hello,
What?
can you hear? Oh, the question is the
What is the event?
of the event of the. Wait, can you tell me the question again? Sorry.
Well, part of the reason I'm asking this is to see who's paying attention. So I'm not going to repeat it. Okay, anyway, that's okay. But our TA Farouk is taking this, writing this down. But anyway, so Zoltran did not get that.
I'm sorry.
Anyway, that's okay. But the point is, I just want people to pay attention. So let me ask the question again. So in the gray question here, what is the event that is being referred to? And let me ask this person, Soliev.
Yes, hello, Professor.
So what do you say?
Yeah, it's about getting 2 heads.
Okay, good. So, okay, so Farouk, we'll take your name down. Your name is Miraziv Soliev.
Yes, that's right.
Okay, so 2 heads is the event in this question. Okay, now in the light blue question, what is the event? And let me ask Kim Sion, what would you say? Okay, so Farouk will pick up Kim Sion. And let me go on to somebody else. Let me go to Andre Vincent. What would you say?
The event of the second question, right?
No.
Oh, sorry. It's basically the event is the probability of getting a head and a tail.
Not exactly. Okay, we won't mark you wrong, but we won't mark you right either.
Okay. Sorry.
Let's ask somebody else. How about Jacqueline Girap something? Jacqueline Girapa something. So what would you say is the answer to the event of the, yeah. Okay, let's ask somebody else. Last person, before I jump in and give the answer myself, Sung Min Lee. Sung Min Lee.
Yeah.
Okay, let me repeat the question. I'll give you a second chance. So the question is, what is the event for the light blue question? Okay, Sung Min Lee didn't get it either. Okay, so the answer is, anybody want to shout out the answer?
Head and the tail.
Okay, who was that?
Bilgun.
I think it was 2 of us.
Okay, what were the 2 people?
Bilgun Batsurin.
And Karina Privits.
What's your second person's name?
Karina Privits.
I don't know if he can hear that. Oh, Karina. Okay, Karina Pritivits. Okay. Okay, good. So yes, so the event here is head and tail. And okay, for the last question, I'll ask Mr. Miura. What is the event for the green question?
Getting at least 1 head.
Okay, good. Okay, Farouk, I hope recorded that. Wilhelm Miura. Okay, so we have identified the events in these 4 different questions. Okay, we circled them here. In the green one, in the light blue one, in the gray one, and the darker blue one. Okay, we circled the events. Now, we also, for the experiment here was the same for all of these questions. The experiment was this experiment here, tossing 2 coins. That we were talking about this experiment for all of these. Tossing 2 coins was the same for all of these. But the events are different. And the first one, oh, sorry. Sorry, I made a mistake. This is different. This is tossing 1 coin. So let's ignore that. So let's just talk about these 3 down on the bottom. This one, and this one. So these are all for the same experiment, all for tossing 2 coins. But we said getting 2 heads, getting a head and a tail, getting at least 1 head. So what I'm trying to get at is what do we mean by this word event? So we can see like it comes at the end of the sentence. So we could say it's the part that comes at the end of the sentence, but that's not the best answer, because I'm sure we could ask this in a different way and it wouldn't come at the end of the sentence. I'm sure we could figure out how to phrase that in English so that it doesn't necessarily come at the end of the sentence. So we need some other definition than just the part that comes at the end of the sentence. But I want to understand, what does this word event mean? What does it mean? We have examples: getting two heads, getting a head and a tail, getting at least one head. We have three examples. Maybe by thinking about these three examples, we can come up with a definition for this word event. And I don't want to just say it's the phrase that comes at the end of the sentence. I don't really want to say it that way. In fact, I want to use in the definition of event, in the definition of event, I want to use the words sample space. So somehow I want to include that, or I want to define event in terms of the sample space. So, can anybody do that? Now, one way to think about it is to go back to this sample space here. Let's just review again. So where is this event, the gray one? Getting two heads, where is that? That's this gray circle here, right?
Yes.
And then if we do this blue one, where is that event? That was these two. And then the green one, what was that? That was this one, and this one. So in general, what can we say an event is in relationship to the sample space?
It's a part of sample
Yes.
space.
Right. So what do we mean by an event? This word part is not what I'm not using. I'm not talking about this word part. But an event, as she just said, an event is a part of the sample space. Each of these events, the gray one, the blue one, and the green one, the events referred to in those sentences, each of those is just a part of the sample space. In this one, it's just this part. In this blue one, it's these two. In this one, it's these three, but they're each a part of the sample space. Okay, so now we have a kind of definition of what we mean by the word event in terms of the sample space. Now, remember I said that I'm going to be using this symbol for sample space. Now, what do we use this symbol for in math? What do we use these brackets for in math?
Group of numbers or group of a set of things.
Yeah, we use it for sets in math. We use these symbols. So the sample space, I should say not just all possible outcomes, but I should write ahead of that. I can't fit it in up here, but I should say that it is the set of all possible outcomes. So maybe I want to write this. But that goes here. So it's the set of all possible outcomes because we're using this and this. So we're talking about it as sets. So this is a set, this is a set, this is a set. We're talking about sets here. So instead of saying an event is a part of the sample space, there's another word we can use when we're talking about sets. Anybody know what I mean? instead of using the vocabulary part, is there another tango we can use? Oka no tango wa arimasu ka? Set no tango. How do we say set? How do you say set in Japanese? I forget. Let's see. Let's look that up. Let's try set in Japanese. Setto suru. That's not right. I guess it might be this one. How do I say that? Anybody know how to say that?
Kumi.
Kumi?
Hi.
Oh, okay. Kumi. Is that the right mathematical word for set?
I don't think so. Just setto. They.
No, I don't think it's setto. Really? I think it must be. There must be a word for that. Set.
Kumi is just like a little bit different.
Kumi is different. Well, how
We
about
say-
this?
We say something like kumiawase.
Shugo. Actually, the word for mathematical in Japanese is called shugo.
Okay, is it listed here?
Someone minutes.
This one?
Yeah, shugo, yes.
Okay, let's see that. Oh, shugo. Okay, shugo. What does that mean? Shugo. Anyway, whatever. Okay, so that's set. Anyway, we're not doing this in Japanese, but I was just curious. Okay, so anyway, we have shugo. So anyway, we have set. Oops, not that. What happened to my list there? Uh-oh. Oh, yeah. Sorry. That's right. So anyway, the sample space is a set. So there's another word. Instead of using part, there's another word that we can use. So instead of saying an event is part of the sample space, what can we say? An event is what? Okay, we can say subset, right? That's a set word, right? So instead of part, we can say a subset of the sample space. Okay, so if you want to say part, you can say part, but I prefer subset. So in this case, the subset is, no, I don't want to do that one. In this case, the subset here is two heads. So two heads is, the subset is just this. So that's the subset. In this case, the subset is head and tail. That was these two. So we could write HT, comma, TH. And that's the subset. And in this case, the subset is the green ones. So it would be HH, comma, HT, comma, TH. So those are the events. So we have this event, and this event. All right, and now we have all these definitions. So we know what we mean by the experiment. We know what we mean by the set of all possible outcomes, or the sample space. So we can have this. If we're tossing one coin, it's heads, tails. If we're rolling a die, it's 1, 2, 3, 4, 5, 6. If we're tossing two coins, it could be this. We said it could be other things, but this one is the most useful way to express it. So we'll say it's this. And then we know what we mean by an event. An event is part of the sample space, or a subset of the sample space. Okay, does everyone understand this? Now, I want, this sounds like, remember I said we were talking about before at the beginning of our course, we had to talk about these things like nominal, ordinal, ratio, and interval. And you probably thought like, who cares about that? And it doesn't seem important and so on. But it turns out that it was somewhat important. And these definitions are more important for this subject. So these words, experiment, sample space, and event, are like the most important for this subject of probability. So let's see why. Let's see why they are useful. So let me save this so I can use it some other time. Probability, sample space, event, and blah, blah, blah. Okay, now let's take a new screen. And let's try to use these words in this case for a new experiment. So let's say roll 2 dice. Let's try that. So let's try taking this, copy it, put it in here. So we're going to roll 2 dice. So the experiment and then we're going to talk about the sample space. And maybe we'll talk about events also. So the experiment here is to make a different color. Okay. Is to roll 2 dice. That's different than we did do toss 2 coins, but we didn't do roll 2 dice. We rolled 1 die, but not 2. And now we're going to talk about roll 2 dice. And now we want the sample space, and as you know, just like before, there may be different ways to express it, but I want to use this. So the question is, what is the sample space? And I'm going to say that that is the sample space. So I guess I need to put like brackets here somehow, like here and here or something like that. But anyway, that's the sample space. Or we can also use this way to show the same thing. I could say this one. Could also use that. Either way, of course, would work. First of all, before we do that though, what does this mean? What does that mean in this picture? Anybody want to explain that or just mention what that is? You have to undo your microphone.
Have you got a 1 and a 6?
Yeah, it means you got a 1 and a 6, right? Okay. It means actually, and we're going to distinguish, just like we said, we distinguished between H, T versus TH. We distinguished between those. We're also going to distinguish between this one and this one. So this one means you got a 6 and a 1, but you got a 6 on the first one and a 1 on the second. And this means you got a 1 on the first one and a 6 on the second. Or you could say a 1 on the red one and a 6 on the white one, whatever. Okay, so these are not the same, just like these are not the same. We're going to say that. So Okay, let me say, what does this mean? So let me ask somebody, what does this mean? So I will ask somebody. Okay, how about Isabella? Isabella Ali Shagoto.
3 and 5. It's an event.
Okay, 3 and 5.
Yeah.
It is an event, but I just asked what does it mean? So it means you got a 3 on the first one or a 3 on the red one, and a 5 on the second one or a 5 on the white one. Okay, good. So that is what that means. So I think it's clear what all of these mean. And this is the entire set of possibilities. There are no other possibilities. This is the sample space, the set of all the possibilities. Because what does it mean? This means you get a 1 and a 1, a 1 and a 2, 1, 3, 1, 4, 1, 5, 1, 6. And then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. And then 3, 1 up to 3, 6, 4, 1 up to 4, 6, 5, 1 up to 5, 6, and 6, 1 up to 6, 6. That's every possibility. Okay, so one thing we can ask is, how many elements are in the sample space? So what's the answer? Okay, let me ask somebody. I want to ask somebody, how many elements are in this sample space? So how about this person? Sun-Yun Oh. Sun-Yun Oh.
Yes, sir.
How many elements are in the sample space?
36.
Okay. 36. How did you get that?
I just counted.
Yeah. There's six columns here, and there are 6 rows. So that means there are 36, right? Okay. So there are 36 elements in the sample space. Okay, now let's do a probability problem, just like we did some before. We did a bunch of questions already. Let's do one now. So let's suppose I ask this question. I'll start out with what color? Green. So I'll start out with this question. What is the probability of getting a sum of 3? Okay, so there's a probability question. It says, what is the probability of getting a sum, getting as a sum? No, yeah, okay, getting as a sum. That's not very good English, is it? Getting a sum, it should be a sum. What is the probability of getting a sum of 3? So first thing is, I want to know what is the event that we are asking about here. So I want to circle the event. So where is the event in this sentence? So let me, does anybody want to answer that?
Is that getting a sum of 3?
Okay, who was that?
I do.
Wait, let's get you. Who are you?
I do
Aidu.
Ito.
Okay, Ito. Okay, Aidu Ito. I think Farouk will catch you. Okay, that's right. He just said it's this part here. This is the event that we're talking about. A sum of 3. Now, let's remember what we said the definition of event was. I already forgot. What is the definition of an event? An event is a what? Part of the sample space or a subset of the sample space. I'll use subset. A subset of the sample space. Okay, I use that. Okay, that's an event, and this gray is some event. So let's identify which part of the sample space it is. So how about this? Is this in it?
No.
No, 1, 1 is not in it, right? That doesn't sum up to 3. How about this? Is this in it?
No.
No. How about this?
No.
Nope.
How about this?
No.
No.
How about this?
No.
No.
Maybe there's nothing in here that sums to 3. Maybe the answer is nothing. Well, that's not quite true, though. How about this? Does this sum to 3?
No.
No.
Okay, I guess we have to give up. There's no answer. I guess there's 0. No, that's not right, right? Okay, right. So, so anyway, here, right? This one sums up to 3, and this one sums up to 3. So we can say these are the two that sum up to 3. So this is the subset of the whole thing, which is our event. So this is our event. So now I think we can probably answer this question. What is the probability of this event?
2/36.
Yeah. So we know there are 36 possibilities. And one thing that we haven't repeated too many times, but we need to keep saying it, is that all of these are equally likely. If they're not equally likely, we can't do this. We can't get this answer. But we're assuming that all of these are equally likely. So we'll sort of talk a little bit more about that later. But I think it's not impossible to argue or to accept that these are equally likely. Each one is equally likely. That is to say, for example, this is not more likely than this. They're both equally likely. Or this one is not more likely than this. Okay, so that's the kind of argument we want to make. And if we accept that they're all equally likely, then we can answer this question. What is the probability of getting a sum of 3? And there are just 2 ways out of 36 equally likely ways. So that must be 2 out of 36. So we got this answer. Okay, let's try another one. Let's try this one. What is the probability of getting a sum of 5? Okay, so first of all, let's identify the event in this question. So how about Kawabata? Can you tell me what the event is in this question? No. Okay. Yusuf, can you pick that up? Kawabata Sirika. Okay. How about Safina? Safina Hara something. I can't see the whole name.
Yes.
Okay. What's the event here?
Is it 5? Sum of 3.
Oh, very good. Okay. Sum of 3. So that's the event in this question. No, sorry. Sum of 5. Okay, you did the wrong answer. Anyway, okay. So here, the event is the sum, getting a sum of 5. Okay, so we want, so now again, an event is a subset of the sample space, and here is a sample space, and the event is a subset. So is this in there?
No.
No. How about this?
No.
How about this?
No.
No.
How about this?
Yes.
Yes.
Yes. How about this?
Yes.
Yes.
So it's these, right? This one, this one, this one. Hope I did that right. Yeah. Okay. So that's the event referred to in this question. And I think we can answer the question now. So the answer is what? How many ways are there? 1, 2, 3, 4. 4 out of?
36.
4 out of 36. Okay, so we got that. Now, how about if I change this to 6, getting a sum of 6, then what would it be? It would be this one, this one, this one, this one, and this one, right? And what would that give me?
5 over 36.
That would give me 5 over 36. And how about, so what is, so which sum is more likely, 5 or 3?
5.
5. Which sum is more likely, 6 or 5?
6.
6. And what is the most likely sum? So this is 3, this is 5, 6 was here. What's the most likely sum when you roll 2 dice?
7.
7, because that's the longest diagonal here, right? So that's going to be the most, notice that on it, that if you say the sum is equal to something, you're specifying a diagonal, because a diagonal will all have the same sum. Like these have the same sum. These all have the same sum. So diagonals are all going to have the same sum. And so if you specify a sum, you're talking about a diagonal, and the longest diagonal is here. So that's going to be the greatest probability, and that's at 7. So 7, that maybe that's why they say 7 is lucky, right? We sometimes think of 7 as being a lucky number. Maybe that's why from this game. I don't know. Okay, but anyway, the probability that the sum is 7 is the highest probability. Okay, does everyone understand that?
Yes.
Now, I don't know how many of you could have answered this question and this question and this question and so on without having thought about these concepts: experiment, sample space, event. Okay, so these concepts have proved to be valuable. They allow us already to do a lot of probability questions. So they're pretty powerful. Okay, so these are very important concepts in probability. So let's do one more of these just for, well, before we do one more of these, let's identify the events using set notation. So what I mean by that is, let's do this. So this event, the event of getting a sum of 3 is going to be a subset, like I said. And then which are going to be the elements in here? 2, comma 1. I guess I can put commas there. Yeah, they put commas in the table below here, so I'll do the same thing. So 2, comma 1.
1,
and
2.
1, 2.
1, comma 2. Okay. So now we're writing it like I wanted to do as a subset. Okay, so can do that. Can identify it like that. And we can do the same thing for the blue. Let's identify that as a subset. So I'll use brackets again, and then I'll put in, so the blue one is what?
4, 1.
4, comma 1, comma
3, 2.
3, comma 2, comma
2, 3.
2, 3,
And lastly,
and
1, 4.
1, 4. And now I've written that as a subset of this, of the sample space here. I can write the sample space like this. I can also write it like this. And now I've written it, this sum of 5 as a subset of these. Okay, so everyone get this? Now, normally we'll do something like this. We might call this F. Just, usually we give them letters like this when we're doing probability questions. We might call this E or whatever. So like we'll say the subset E or the subset F. Okay? So, and I'm sorry, we'll say the event E and the event F. Okay? So the event E, the probability of that event is 2 out of 36. The probability of the event F is 4 out of 36. Okay? Now we can, why not do this in a kind of more mathematical way? So I can do it in a slightly looking more mathematical by doing this. Equals, and then we can do this, P of E. P of E just means the probability of E. So the probability of this E is 2 out of 36. And here, for this one, we can make it look a little more mathematical by saying the probability of F is, because I called this F, so the probability of F is 4 out of 36. So that's just making it into a more kind of more math notation. So, but anyway, we can write this. The probability of E is 2 out of 36. Of course, normally we would write it like this. Probability of E equals 2 over 36. Right? So that just says what we've already said, that the probability that the sum is 3 is 2 over 36. Okay, is everybody okay with this?
Yes.
Okay, now maybe we can even write a formula for these calculations. So let me use one thing here, and that is, let me say, whenever I have a set, let's suppose I have a set E, like this set E here, then I can say N, let me use a different color here. I can say N of E just means the number of elements in E. So here there's how many commas are there in E? I'm sorry, no. Sorry, I don't mean that. Let me go to here. So we have this comma here that separates these two elements. And we have this comma, and this comma, and this comma separates these 4 elements. Okay? So how many elements are in F?
4.
4. And how many elements are in E?
2.
2. Right? So this is the one element, and this is a second element. This is one element, a second element, a third element, and a fourth element. Okay? So N of E just means the number of elements in E. Okay? So I'll use that symbol. N of E means number of elements in E. We use this, N of E. So how about if I said, let's call this whole thing here, this whole sample space, let me call it S. So I'll write this, S equals this whole sample space, the entire sample space. If I asked you this, N of S, what's the answer?
1.
No.
36.
36. How many elements are there in here? 36. 1, 2, 3, 4, 5, 36. So we would say this, n of s is 36. N just means the number of elements in the set. So if I had just this, another example has nothing to do with probability. If I just had a set A equal to, 3, 7, A, or A, B, 9. How many elements are there in this A?
5.
5. So we would say n of A, that just means the number of elements in A, is 5. Okay? So that's just that symbol means the number of elements. But now maybe we can make a formula for probability. So what do I mean by that? Well, maybe we can say if we have an event E, not necessarily this E, just any E, if we have an event E, how do we calculate the probability? Well, how did we calculate the probability of this E? It was 2 over what? 2 over 36. Where did the 2 come from?
The number of events.
The number of elements in E. And where did the 36 come from?
The total.
The number of elements in the sample space, right?
Right.
How about here? How did we get this number, 4 over 36? Where did the 4 come from?
Number of
Number of elements in
F.
F. And where did the 36 come from?
The total elements.
Total number of sample space.
Yeah, the number of elements in S, right?
Right.
The number of elements in S. We also did this one here. This was for, I don't know, what was this? This was when the sum was 5. This was when the sum was 6. So when the sum was 6. So where did that 5 come from? Well, anyway, let's not do that. Okay, so what is the formula that we're using? If we want to know the probability of E, we have to count out how many elements are in E and divide it by what?
By the number of
elements in the sample space, right?
Yes.
So we can say n of E slash n of S. Sorry, that's wrong. E divided by n of S. So now we have a formula. This is exactly what we did. We just counted how many elements were in E, that was 2, and how many elements are in the sample space, that's 36. Same thing here. How many elements are in F, that's the number of elements here, or the number of elements here, and divided by the number of elements in the sample space. So this formula allows us to calculate probabilities. And it's not just for this one, for also the previous whiteboard that we had would work just as well. Let's copy this. Let me select this and see if it works still. Copy it. Let's go back to the other whiteboard we had, which was, let me open that. That was here. Let me open this. I think we're going to have to save this one first. We'll save this as okay, and then let me go to here and open up this one. Bring it up with Paint. Open with Paint. Okay. Okay, this one let's paste in that formula, which is here. Now let's see, does it work? We did something here. Let's try this one. So this one, the green one, what was the experiment here though? What was the experiment for this green question? Where's this one? Tossing 2 coins. So what was the sample space for this one? It was here. And how many elements are there in the sample space?
4.
4. So this is S. Maybe I should write it. This is S. S equals this. Okay, and there are 4 elements in S. And the event of at least one head was these 3, the underlined green ones, which we didn't actually write out. So let's write it out here. So the event, let's call it E. Just call it E. E equals what? HH, comma, oops. HH, comma, I guess I could have put commas there, but HH, comma, HT, comma, TH. And then that. Okay? So that is E. This is E here. Getting at least one head is this. Now let's use this formula to calculate the probability of this. We already know the answer is 3/4, but let's use this formula. So we need N of E. How many elements are there in E?
3.
3. And how many elements are there in S?
4.
4. So this formula works just as well here. We said the answer was 3/4, and here it's 3/4. So this formula is going to be our formula for calculating probabilities. So what's the formula? That. Okay, so everyone get this?
Yes.
Now, but don't forget that in order to come up with all of this, you need to think about experiment. So experiment, tossing 2 coins. You need to think about sample space. So this is the sample space in this case. And then you need to, when you see the question, you have to say, oh, what's the event? Oh, it's here. And then how can I write it like as a subset of the whole sample space? So I did that here. And then I can just count how many elements are in here and how many elements are in the sample space. And then I can do the question. Okay, does everyone get this?
Yes.
Okay. So we've talked a lot and we've done a lot, but I want everyone to make sure that you're clear about these 3 words. So the 3 words for today, today's 3 big words are, what are they?
Experiment.
Experiment,
Event.
sample space, event. And of course, maybe the biggest word is, okay, probability. So but anyway, these 3 words, experiment, sample space, event. That's what you need to know today. And, this formula, it's good to know that too. But anyway, these 3 words, you need to know what we talked about. Now, one thing, does this always work? No. this formula doesn't always work. For example, suppose I had used this as the sample space instead of this one. Now, how many outcomes are there in this sample space? If this was S, how many outcomes are there?
3.
3. So this is not going to work. It's going to give us a different answer, and it's not going to be the right answer. So I said, this is a valid sample space, and so is this, but this one is more useful. And usually the more useful one is the one where each of the outcomes is equally likely. These are not equally likely. Now, maybe we wouldn't even know that. Maybe we don't know that these are equally likely and these aren't. And maybe it's not even easy to know. But if we can know, so if we can decide that these are all equally likely and these aren't, then this is going to be the better sample space to use. Now, maybe it's not intuitively obvious that these are not equally likely. So it's sort of not intuitively likely. That's right, it's not intuitively obvious. I wouldn't have, if I had just come to this problem by myself, somebody hadn't taught me, I would have thought that these are, why aren't these equally likely? It seems like they should be equally likely. So it's not to everybody, it's not completely obvious that these aren't equally likely. So somehow we have to know that these are equally likely and these aren't. And I don't know how we know that really. But by the way, one thing that you can know is you can know that these can't both be equally likely. If these are equally likely, these aren't. Because if these are equally likely, then getting one head means the two blue ones. And if these are equally likely, then getting one head is 1/2. Probability is 1/2. So it can't be 1/3. So if this is equally likely, these aren't. And if these are equally likely, then this isn't. That much we can know. But I personally, I don't even know how to show or know that these are not equally likely and these are. But somehow we have to know that. If we know that these are equally likely, then we can use this sample space, we can use this formula. Now, we would get a different answer if we said these are equally likely. We wouldn't get the same answer 3/4. So somehow, as I said, we have to know that these are equally likely. And I don't even know how to know that. So maybe you just have to believe it. I don't know. There must be some way to know it, but I actually don't know that. But anyway, once we identify an equally likely sample space, then we can use this formula. Okay? So this formula is very useful and very powerful, but it does depend on the sample space having all equally likely outcomes. Okay? So that is the end of our first lecture on probability. Now, what I would like to do eventually is use these concepts to say the following. I know we're just about out of time, but let me just say, suppose we had two investments. Let's call them A and B. And suppose we went to an expert, and by the way, you can do this in Yahoo Finance. So if you go to Yahoo Finance, let me just show you. Here's a stock that my friend recommended I buy. It's called SESN. Okay, so let's look at this, or we could look at Tesla, but I'll just look at this stock. And if you go here, there's a section called Analysis here, Analysis. And here, under the Analysis section, you can find here, here, you can find that they have some professional analysts who say that it's a strong buy. So in December, they said this was a strong buy. And one person said it was a buy, but not a strong buy. So anyway, you can look this stuff up on Yahoo Finance, for example. So anyway, going back to here, suppose we have two investments and we go to some experts and they say that this one is going to become $100,000 or it's going to become $200,000 or it's going to become $50,000. And let's suppose we have to put in initially $75,000, and then after 1 year, we talk to the experts, and they say, well, it might go up to set 100, might even go up to 200, and it might go down to 50. And this one, the analysts say, oh, there's a 25% chance that it will go this way, that it'll be this value, and there's a 35% chance that it will be this value, and there's a what's left over here, 40% chance. There's a 40% chance that it'll be this value. And then we have another investment, and let's say it can go up to 150 and 200 and down to 20. And then the analysts, sort of their average estimation is there's a 20% chance it'll be this, and there's a 20% chance it'll be this, and there's a what is left over, 0.6 chance that there's this. So now we want to guess which investment is kind of better. And hopefully by the end of our last class, we'll be able to use probability to answer this in a precise way. Okay, so we'll take these are probabilities, and these are probabilities. We want to use them. Anyway, we'll come back to that later. So at least I want to cover that much in our class, though, before the end of the semester. Okay, that's all for today.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.
We will have your favorite Khan Academy. We will have some assignments there, so pay attention to that.